Thank you, and I'll just ask the speakers to turn on their videos so that people know who they're speaking to or remember who they're supposed to be speaking to. Thank you. Okay, so we have a couple of different viruses that we were talking about, malaria and COVID-19. And David and Chapin, you're on the panel, so feel free to join us. And there we go. So I was going to ask a question, I think first, while we're waiting for other people to put some questions in the chat, or let me know that they have a question to the COVID-19 researchers. So we've talked about vaccination at the population level, and we talked about vaccines, the mRNA vaccines in host. And so Chapin used the standard dose time frame between doses. And I can't remember what you used, Carolyn, but David used the 16 weeks and then varied it for the summertime. And I was just wondering if people could comment on whether they've tried different dose times and how that has affects the results, because there are some immunology studies that have come out to say that longer time frames between doses is better. And Lauren, feel free to pipe in too, because I know you've worked on this too.
I can give a quick answer based on the intuition gained from our model. So just if we were to do an additional, if we were to extend the time between doses in our model, we would find that at the 8-month milestones, there would be more immunity remaining because the time between doses isn't going to change the long-term decay. And so I think it would be advantageous in the long run to extend the time between doses based on that intuition.
Yeah, and I was just going to say, like, from our modeling perspective, one thing that we didn't do, which is another limitation of what we can say quantitatively, is to say that the spacing is in any way coupled with the strength of immunity that we assume for 1 or 2 doses. So one thing we could have done, for instance, is to say, like, if we delay by 4 weeks versus 16 weeks, does that tie into the assumptions that we make good that second doses, which I think, Jane, is what you're referring to, how there does seem to be like the actual immunity might be different depending on the spacing. So we didn't do that, but what we do is we looked at a range from essentially 3 to 4 weeks to 16 weeks to, I think it was 24, and then to what we call 1 dose, which is not entirely accurate. The second dose would have come about eventually, but we just take it to mean a very, very, very long interval between doses. In terms of what we did.
I'll just add, from our model, when we space out the doses, of course, you have some waning immunity and then you boost it with the second dose being later, but our supply of vaccine is more representative of what Canada has. So we had much more supply effect happening than dose spacing effect. So because we had more supply, giving 2 doses quick is advantageous in our model.
From my point of view, I'm looking at things from a heterologous vaccination instead of just time between doses. I think it's really important to pick a prime virus that is suitable to give it a little bit more of the memory boost before the second dose comes in. So I think the question of time and also the type of vaccine that you mix and match is really important. If you were to choose an adenovirus as a prime vaccination first dose, then you would give it a bit more time. But if you were to use the mRNA as your prime, then the time is a little shorter. There are some data available coming out of Oxford, and this is a subject that we are interested in finding out whether mix and match works and what are the time in between that is optimum for us to have a good end result.
I think one thing that I'll bring up that David added earlier is that human behavior is obviously a big component in this, and trying to capture people at exactly that optimal timing may or may not be what the ultimate goal should be, considering in terms of where the protection falls. And so I know that's something that David's seen in the model with the variability not necessarily lining up, and that there's probably some other explanations coming out of that.
I totally agree with that. I also want to add, I guess, to that thought is, I think when we look at the Canadian population, there's also the question of, do you want the maximum immunity for an individual, or do you want to space your doses to have the highest level of population immunity as quick as possible to reduce the cases? And there were some counterintuitive results in the model that way, but I do think probably trying to get the population immunity up more quickly is more important than trying to get individuals' maximum immunity up. As far as a population level prevention, I'm sure individuals want their immunity as high as possible.
So going along the lines of talking about immunization, and James brought up the heterologous immunization. We look at 2 doses of one type of vaccine, but we also can model in-host infection and then vaccination, or vaccination and then in-host infection. And Lauren, you've done some work on this too, like looking at vaccination and infection in different combinations, I guess, looking at antibodies too. I wonder if you want to comment on some of the work that you've done.
Sure, I can try to comment on that. I think it's a bit needing good within host data on what those levels are protection wise in terms of either vaccination or some sort of transfer, and versus natural infection. That's really important to get sort of precise answers out of the model. In terms of malaria, there's a little bit of this sort of different idea, because you have this multiple protection in multiple directions, because the parasite is more complicated and there's more avenues of where, say, partial protection can come from. And I think protection in general is not as well understood as in many viral infections, which I still think it's not fully understood there, but just the level of understanding is less in the field of malaria in terms of what actually provides protection in certain, certainly in terms of the disease, naturally acquired disease protection that's out there. But there is this idea of sort of this repeated boosting and repeated buildup, and is that going to be the acquisition of additional immunity against additional proteins that kind of builds over time, which is sort of what was built into our within host model, that phenomenological version of that, versus some sort of boosting and waning and boosting of immunity that's happening there. And in some ways they can produce kind of similar looking effects on what's happening in that way. So maybe there are sort of multiple axes of protection that need to be considered, even in the context of maybe simpler pathogens where we might understand what's happening. And that's why the within host data and really thinking about that carefully is so important. And I think the other thing that I haven't really done any work on, but would want to bring up, is the sort of heterogeneity and susceptibility and how that changes through the course of an infection, and whether protecting a lot of people earlier is really going to actually get an extra boost there, because you really get the opportunity to protect the more susceptible individuals there. We do know there is variability between people in terms of their propensity for disease, whether that's age related or some other comorbidity related or something like that.
I think so, touching back on like strains, different strains and immunity. So I know, Carolyn, you've looked at different strains popping up, or like this evolution type of aspect. And so have you thought more about distributions of immunity in a population when you have all these different strains that can pop up, and how this affects like immunity at the population level?
Yeah, so that's what we're trying to do now. So like you're saying, we did it in a really toy way before, where this potential evolution just, which sort of you can think of like a strain popping up, but we didn't want to say that because that makes it sound like it's a better evolutionary model than it is. But we assumed that that was coupled with just a transmission increase, but we could have done it different ways. We could have said maybe that's coupled with a decrease in this protection that people have, sort of representing more like evading immunity or something, or your susceptibility goes up now in the face of this evolutionary event. But I think, it's not completely out of left field because we have seen a lot of variants pop up have increased transmission potential. So we sort of thought it was like a worst case scenario from that perspective. But what we're trying to do now is explicitly, so today we really only ever had one infection group in terms of strain, whether that's primary or secondary infections. Obviously we have those stratifications, but now we're going to explicitly have different strains in what we're working on. So we're going to try to preserve sort of the original strain and then a couple of variants, alpha, delta, and sort of try to capture this sort of sequential replacement, and then maybe have place for a new one to come in. And then exactly like you're saying, I think it's going to be really important at that point, and that's what we're working on now, to say, and the life history of infection may really play differently in terms of how susceptible you are. So we want to try as much as possible in compartmental models to keep track of, have you had a prior natural infection? Have you had a natural infection followed by a vaccine? Have you just had a vaccine? We're even going to try to possibly stratify by vaccine. So we're trying to draw on analyses that are coming out now in terms of protection that these different sequences offer to different strains to feed that in. But yeah, so I don't have a lot of insight now, but just to say, I think it's something that is going to be important that we're trying to work into future work.
So just a reminder to everyone that if they have some questions or things that they would like the panel to discuss, they can put them in the chat. I was also going to think about, or I was going to discuss this whole like in-host, between-host type of link. And when we look at mutations, or we look at different, individual immunity, vaccination, or disease-induced immunity, we often talk about immunity in terms of protecting against infection. And we have touched on protection against severe disease today, as opposed to protection against infection. But there is not a lot of information out there on T-cell memory development or long-term immunity outcomes. And so I was just wondering if people have, if you guys, any of you have some things that you've thought about by incorporating that type of outcome in-host or in between host models, and maybe what kind of data you think would be the best to get, apart from just measuring T cells directly, but if you've thought about, other types of data that might be more readily available.
So I will say that in the context of malaria, we get a little bit of we get to sort of abstain a little bit from that question, because the main disease state is when the parasite's in the red blood cell, and the red blood cell doesn't have the MHC class 1 that allows the T cells to bind. So it's sort of in an immunologically privileged state for most of its time. There are questions about, sort of long-lived T cells in other states like the liver stage that could be important, but the level of parasites is much smaller there. And of course, there is questions about T helper cells and what those, the context of that in terms of, antibody mediated. But I would say in terms of sort of killer T cell dynamics, the malaria communities gets to kind of step away from that question a little bit, but I think it's really important to think about how to incorporate that long-term and sort of changing or waning immunity over time. And I don't have a good answer for it.
Back in the day before COVID, we were trying to do a little bit of this in the context of measles. And one thing I thought was interesting that I think there is data on now is looking not just at sort of either antibody levels in the blood or sort of the most immediate front lines of, mucus in the throat or something like that, but also looking at what's happening in draining lymph nodes and other regions of the body. There are maybe sort of more of these storage repositories and less these sort of immediate attackers. So I think finding correlates between those markers and what's happening in more accessible tissues, and then the clinical protection is sort of interesting. And we were trying to use some of that in the within host measles stuff that we were thinking about. But yeah, and then of course the question was, is it these memory cells or memory B cells or plasma cells, and what's happening with measles too, when you were having this wipeout of memory from past infections that had been seen. But like I say, I don't, I'm an immunologist, don't know the answers to this, but yeah, I think some of these different compartments might be interesting to start getting temporal data on.
Yes, you can also, oh, sorry, go ahead, Jacob.
I was going to say something a little bit orthogonal, so you can finish your thought. I don't want to interrupt the conversation.
Oh, I was going to say too, like just thinking about seroprevalence estimates where you have distributions of immunity against infection, distributions of immunity against disease. David, have you thought about, and Lauren too, because I know you've worked on the model, how when you have that distribution of immunity that you showed, if you have less green and more blue, is it really going to have that big of an effect on memory, or just like the change or the risk of the population being infected when you have immunity against disease versus immunity against infection? Maybe you won't see that much difference in hospital. You'll see more cases, but you won't see really much difference in hospitalizations, things like that. So maybe there is a level of vaccination that is similarly protective, with just protection against severe disease in the population, that can also just give you the same outcomes in terms of protecting healthcare demand.
Yeah, I think to partially answer your question, but I think maybe partially missed the question. I think it does matter, and we do find sensitivity in our model to whether we have natural infection or vaccine infection, and how much protection from severe disease. And the metric you choose to measure with is really important. So if you're just trying to suppress all infections, you'll probably choose a different strategy than if you're trying to suppress only severe infections. So I think that's really important. And I do think there could be, speculating, cases where lots of mild infection would be superior to trying to vaccinate people. And there can be counterintuitive results, but I'm just speculating.
Chapin, you can move to your comment. You like?
Yeah, I was just going to say, in some of the data sets that I gathered, some of the clinical data sets, those papers have a smaller subset of individuals that throughout the course of their study did contract SARS-CoV-2. So either before the vaccine, they had it and then went through their study, or they received 1 or 2 doses and contracted SARS-CoV-2. And these papers analyzed those individuals separately. So I would be interested in developing a model where an individual, a within host model where an individual is challenged by the vaccine, and then see over similar timescales, maybe even 360 days, how their cellular and humoral immunity compares to that of not vaccinated. There's quite a bit of literature suggesting that those that have fully recovered from SARS-CoV-2 have a lot higher immunity than from the vaccines, but it would be interesting to do an explicit comparison.
I do see a couple questions in the chat. And so the first, I think, is similar to a question that we just discussed in terms of vaccinating broadleaf. So it says, I'm curious about the optimum of viral evolution that Dr. Wagner talked about. I've heard that in some diseases like chickenpox, that if a certain herd immunity can't be reached, that it's not advantageous to vaccinate broadly because disease is more severe in adults. Is there a parallel to COVID-19?
Yeah, I think again, this is like the complexity of thinking about something within a host at the population level. And there was a really nice paper. Jenny Levine's the first author for COVID-19, thinking about sort of what happens in terms of this being an age, age stratified disease, and what does the future look like if eventually the infections are dominantly in children, in terms of similarly, I guess, to how chickenpox used to play out in theory. But so yeah, I think there are some parallels there, in the sense that, like most coronaviruses that are endemic, eventually we probably would reach a scenario where people were first encountering it as children as opposed to as adults, which is probably why a lot of the morbidity is playing out now. I was actually just reading about chickenpox yesterday. For some reason I went down that rabbit hole, and I think I saw some arguments anyways that there definitely are advantages to going via the vaccine in terms of reducing morbidity in children, since it is pretty non-trivial, with the idea being, of course, you want to, obviously, like in the startup phase, you can imagine a vaccine program. You don't want to miss people who might then go on to acquire it as an adult, but sort of the idea is thinking about the longer term steady state, reaching that immunity as a child is also beneficial in terms of not getting shingles as an adult, but minus the problems that come about with getting the infection as a young person.
Thank you. And I think we'll go to the next question. There's a lot of evidence from history on effects of prior immunity from influenza epidemics, including cross protection, original antigenic sin. I wonder why models on COVID overlook that. Could you comment on this? I think that might be referring to immunity against other coronaviruses like the common cold that could be related.
My response is almost a little bit of a cop-out response, and it's just that if I had really good data on that, I definitely would incorporate it into a model and explore the effect. Like if we could tune a single knob where some sort of prior infection from a maybe related disease but not the same disease proffered some sort of long-term immunity for some other disease like COVID, and we had the data to support those people and their immune response, and I think we could certainly model it and fit to the data. Otherwise, we could, of course, we're free to come up with a model, but then we're tuning knobs in our paper, and we don't necessarily know if it's realistic. So I would almost turn the question on its head and say, of course, I would love to do that, but without really strong data to guide how we deal with the math, I would be really hesitant to do so.
Yeah, I think you can think about it in terms of like an applied math type of exploration, where you can say start a model like Carolyn and David's and Lauren's, because Lauren's worked on it too, with different initial conditions, and see how the outcomes would change after you go through all of those aspects. But I think it's a big computational problem. In the beginning of COVID-19, there was work that went into looking at cross protection against common cold coronaviruses and SARS-CoV-2. And while they saw some relationships between the immunity, they weren't able to really quantify, as far as I can remember, any sort of protective capacity against infection or disease. I would have to go back into the literature and have a look to see if anything's been updated. I see that it's 3:01, so if anybody has a last comment, they can feel free. Anyone on the discussion panel?
So I want to kind of circle back a little bit on the memory B cells and memory T cells that you mentioned earlier. I think, early on in the pandemic, we had a lot of trouble getting high quality data, even for, IgG and IgM. As we are more settled into the pandemic and we get more and more quality data, I think we should start looking into more detailed models of, say, CD8 positive evasion and things like that. I'm thinking of this from an immunotherapy point of view, because I used to work on oncolytic viruses, and one of the major component of that is to find ways to kind of cloak some of these viruses so that we are able to destroy the cancer cells, right? There's a lot of immune evasion that we have to play with, and a lot of gene signaling that we have to be able to understand. So I think there's a lot of value as we start getting data on these T cells, memory T cells, that we look into details of how these CD8 positive are being evaded. I think that's the value going forward with mathematical modeling.
Yeah, and I see so much more in-host modeling happening now, given all of these different new data sets that have come out from COVID-19 studies. So I see a lot of growth happening in the next, few years to decade to many decades, even with the advancements in all the different technologies for measuring all these things that have happened very recently as well. I'd like to thank all of the panelists and speakers, Carolyn, Lauren, Chapin, David, and James. And I think we have a 15-minute break now. Is it 15 minutes?